We next consider a special case of two-dimensional motion. A particle moves in a vertical plane with some initial velocity, but its acceleration is always the free-fall acceleration g, which is downward. Such a particle is called a projectile, meaning that it is projected or launched, and its motion is called projectile motion. A projectile might be a ball or even a person, but it's not an airplane or a duck in flight. It has to be something that's under the influence of gravity only, no air resistance or lift from wings.
You might have noticed something that all those projectile motions had in common. They were all parabolic in shape. Some of them started at this point of the parabola and went down like the snowboarder jumping off the cliff. Others started low and ended a little higher than where they started, like Steph Curry's shot into the basketball hoop. And others landed and started at the same height. Some of the parabolas were taller. Some of the parabolas were more stretched out. But they're all parabolic in shape. Now remember, that is for free fall projectile motion. Remember, free fall means neglecting the effects of air resistance. Now it is true that the football thrown by Colin Kaepernick and the basketball thrown by Steph Curry, they did all undergo a little bit of air resistance and were affected slightly by air. But for most of the problems, unless it says otherwise, we're going to neglect the effects of air resistance, and we are going to assume that the object is in free fall, meaning that gravity is the only force acting on it. There is no force of air resistance. And of course, gravity only works in the negative y direction. Here's where the projectile is launched. It's going to have some initial velocity, and it will have a component of velocity in the x direction and a component of velocity in the y direction. If we know this launch angle and the initial velocity of the projectile, we can calculate what the x and the y components are. You'll want to keep in mind that when we draw the vectors tail to tail, this is what it looks like. This is what it looks like. But we could have drawn them head to tail just like that. And if you envision that triangle, this is the triangle that we're going to use for our analysis here. The cosine is the adjacent over the hypotenuse, and the sine is the opposite over the hypotenuse. So we can solve those equations for v initial x and v initial y, and we see that the x component of velocity is the initial velocity times the cosine of the launch angle, and the initial velocity in the y direction is the initial velocity times the sine of the launch angle. Because we're neglecting the effects of the wind and the air, that means gravity is the only force acting on this projectile as it flies through the air. And since gravity only works in the vertical direction, that means the horizontal component of velocity is going to be unaffected by gravity. If you notice here, at these various time points in the flight of the projectile, the velocity of the projectile is shown along with its components. And if you notice, the x component of velocity anywhere in the path of flight is the same. It is not changing at all. However, the y component, as it rises in the air, it slows to 0, and as it falls back towards the earth, it increases in magnitude because of the force of gravity acting in the vertical direction. And an interesting and very important idea comes out of this, and that is the fact that the x and the y velocities have no effect on one another. Whatever this initial component of velocity in the x direction is at the beginning, it's going to stay the same, and it doesn't matter what the y component is. The x component is the x component, period, and it doesn't change. Likewise for the y, the velocity in the x could be anything, but the velocity in the y will change at 9.8 meters per second every second because of gravity. In your textbook, there is this picture that is a stroboscopic photo, which means it's taking pictures at intervals of time, and both of these balls are released at the same time, and you can see that 1, 2, 3, 4, 1, 2, 3, 4 pictures later, they're at the same height, and 6 pictures later, they're at the same height, and 8 pictures later they're at the same height, and so on, even though this yellow ball has a velocity in the x and this red ball does not. Let's see a video of this exact experiment.
Both balls fell in the y direction at the same rate, regardless of their x component of velocity. Here's an experiment that was shown to me when I was in college. My instructor called it the monkey and the hunter, but here at the MIT physics department, they call it the monkey and the gun. So that tall stand has an electromagnet, and it will release the monkey at the same instant that the ball is fired from the gun. Now, if there was no gravity, of course the ball would just travel in a straight line. The monkey would hover in space as soon as it's released, and of course the ball would hit the monkey. But there is gravity. Both the ball and the monkey, since they're both beginning free fall at the same time, they will both fall the same distance and the ball will still hit the monkey.